Welcome back. This is Machine Learning lecture number 2. Let's start by reviewing basic concepts we've already seen from lecture number 1. Feature vectors X provide the context for a classifier to make predictions. They are vectors. They belong to RD, so they are d-dimensional vectors in general. D equals 2 for points on the plane, as we've already seen. We have labels or targets or outputs Y that are plus minus 1. The tasks in machine learning are illustrated by a training set, a supervised learning task, where you are given the input and the corresponding output that you want, and you are supposed to learn a regularity between the two in order to make predictions for future examples or inputs or feature vectors X. So the training set, as we've already seen, is denoted by S subscript n, where n refers to the number of training examples that we have. And it is a collection of pairs of the input feature vector, where the superscript I denotes the ith example, and the corresponding label, and we assume that we have some number n of them. So that is the task as given to the algorithm. Now, a classifier is a mapping that takes as an input a feature vector. So it maps any point in RD to plus or minus 1 label. So if we apply the classifier to a particular point, we will get either plus or minus 1 label, for example, 1. Okay, so a classifier essentially divides the space into two halves. So we can look at, we've seen shaded areas on the plane that corresponds to the set of positively labeled points on the plane. So this is then the set of all X in RD such that the classifier returns plus 1 label, and similarly for the negative half. Okay, and those together comprise the RD space. All right, now once we have a notion of a classifier, we need to be able to evaluate how good that classifier is. And we've seen two ways to measure how good a classifier is. One that we have access to, the training error, and the other one that we really want to minimize, which is the test error. The training error was calculated by big E, subscript n, refers to the number of examples that you are using to calculate the error. It's a function of any classifier. I pick any classifier. I can evaluate the training error for that classifier, and it is the fraction of misclassified examples on the training set. So we take fraction, divide by the number of training examples, sum over the training examples, and for each example, return plus 1 when there's a mistake and 0 otherwise. So we apply that classifier to the ith training example and compare it with the ith label as given in the training set and ask whether this discrepancy is true. If it's true, then this returns 1 if there's an error and 0 otherwise. All right, test error is defined exactly similarly over the test examples, and now we typically drop the n there, assuming that the test set is relatively large, and it can be measured in principle for any classifier. So defined similarly to the training error, but over a disjoint set of examples, those future examples that you actually wish to do well. And much of machine learning, really, the theory part is in relating how a classifier that might do well on the training set would also do well on the test set. That's the problem called generalization, as we've already seen. Okay, we can affect generalization by limiting the choices that we have at the time of considering minimizing the training error. Okay, the choices that we have, the set of hypotheses, set of alternatives, is also called the set of classifiers. So our classifier here belongs to a set of classifiers, capital H here. That's not the set of all mappings. It's a limited set of options that we constrain ourselves to. Let's look at this geometrically, just as a review here on the plane. So each x here has two coordinates, x1 and x2. So it is clearly a vector in 2D, where d is 2. And its training example is given as a point here. So here we have a training example. Let's say it's the first training example with the associated label. And in this case, the label is -1. That defines the task for our classifier. This is how the supervised learning task is illustrated. A classifier then is a function that we wish to learn, select from our set of classifiers such that it does well on the training set. Okay? So here a classifier, age, is a linear classifier, divides the space into two halves linearly, where the shaded area corresponds to all the points in the 2D plane that the classifier returns +1 and the rest -1. So this classifier would have a training error equal to 0. It correctly classifies all the training examples. Now, the real task that we wish to solve is to correctly classify those test examples that we have not yet seen. And the trick here is to somehow guide the selection of the classifier based on the training examples such that it would do well on the examples that we have not yet seen. So in order for this to be possible at all, you have to have some relationship between the training examples and the test examples. Typically, it is assumed that both sets are samples from some large collection of examples as a random subset. So you get a random subset as a training set, and then the rest are considered as test examples. Okay. Today, we're going to limit our choices of the classifier to the set of linear classifiers and just assume that since that is a restricted set of classifiers, that if we do well on the training set, we will also generalize well. We will return to the question of generalization more formally later on in this course. So what is this lecture going to be about? We're going to formally define the set of linear classifiers, the set H, a restricted set of classifiers. We need to introduce parameters that index classifiers in this set so that we can search over the possible classifiers in the set. Then we'll talk about linear separation, what a linear classifier or the set of classifiers can and cannot do. So what exactly is the limitation? How are we constraining the set of classifiers? Once we understand that set of classifiers we are operating with, we need to define a learning algorithm that takes in the training set and the set of classifiers and tries to find a classifier in that set that somehow best fits the training set. We will consider initially perceptron algorithm, which is a very simple online mistake-driven algorithm that is still useful as it can be generalized to higher dimensional problems. So perceptron algorithm finds a classifier h hat, where hat denotes an estimate from the data. It's an algorithm that takes as an input the training set and the set of classifiers, and then returns that estimated classifier. Okay, and then we can apply that estimated classifier on any new example to get the predicted label for that point. All right, let's try to understand the set of linear classifiers. In particular, let's take a specific linear classifier. It divides the space into two halves linearly. So on one side, the classifier says that all the examples are positive, and on the other side, they are labeled negative. The dividing line here is also called decision boundary. In 2D, that decision boundary is a line. If x was a one-dimensional quantity, the decision boundary would be a point. In 3D, it would be a plane. And in higher dimensions, it's called a hyperplane that divides the space into two halves. All right. We can change the linear decision boundary here and the linear classifier by moving the line around. So here's another example of a linear classifier. And again, the shaded side is positive and the unshaded one is negative. And by drawing these lines in this 2D space, we get the set of linear classifiers over the plane. All right. So now we need to parameterize the linear classifiers so that we can effectively search for the right one given the training set. So let's see how we can index and parameterize these classifiers. All right, so let's start with even a more restricted version, a set of linear classifiers through origin. The only difference here is that that dividing line now is not arbitrarily placed in this 2D dimensional space, but it has to go through origin. So for example, that line could look like so. So the equation for this line would be the set of all points that satisfy an equation for a line through origin. To define that, we need to introduce two parameters, theta1, that multiplies x1 coordinate, and theta2, that multiplies x2 coordinate, and that is equal to 0. So you fix the parameters, theta1 and theta2, that fixes what that line is, and all the x's here, x here is a vector, that satisfy this equation lie along this line. So this is again the decision boundary. All right, we can write this in a vector form by introducing now theta as a vector with two coordinates, theta1 and theta2. And x here is also a vector with two coordinates, x1 and x2. All right, so we can just write down the decision boundary as all x, such that the inner product or dot product between theta and x is equal to 0. Okay, so from this equation, you can see that the parameter vector theta is orthogonal to all the points that lie on the decision boundary. So if we take a point here and look at the vector from the origin, then theta must be somewhere here along this orthogonal line. Okay, so now let's look at the theta.x as a linear function. So this is a linear function. Parameter vector theta is fixed. X varies, so it's a linear function of x. It is positive on one side of this line and negative on the other side. So let's just pick that this side it is positive and on this side it is negative. All right, and it's exactly 0 along the decision boundary. All right, so now we know, based on this choice, which direction theta must be. Theta must be oriented in this direction, because if you take any point here, for which the linear function takes a positive value, and you look at the vector of that, then the inner product between that x and theta is positive. And it's negative for any point here. All right, so now we have parametric way of writing the decision boundaries. And we know which side is a positive one and which side is a negative one. This now allows us to define the set of linear classifiers through origin. Okay, so let's make that a little bit more precise. We have a classifier now parameterized by the vector theta. So each choice of theta defines one classifier. You change theta, you get a different classifier. It's oriented differently, but it also goes through origin. So that classifier is now simply the sign of theta.x. The label that it returns is a sign of that linear function theta.x. Okay? And in general, theta lives in d-dimensional space, as would x. So this is now the set of linear classifiers through origin. All right? So all the choices of, you try all the parameter values, you will get different classifiers, and all the classifiers that you can get by varying the parameter theta are linear classifiers, and the whole thing is the set of linear classifiers. All right, note that this association between the classifier and the parameter vector theta is not unique. There are multiple parameter vectors theta that define exactly the same classifier. Okay, but each linear classifier through origin has at least one, in fact, many parameter vectors theta that correspond to the same decision boundary, same decisions. Okay, so what is that degree of freedom here? If you look at that linear function, the classifier only cares about the sign of that. So however we multiply the value of theta here, we will get the same classifier as a result. So the norm of the parameter vector theta is not relevant in terms of the decision boundary. But we will make use of this degree of freedom later on. Okay? One additional point that we can understand is that the theta.x is the degree to which we classify the example positively or negatively. That degree only changes when we move orthogonally to the decision boundary. If we take 2 points here that are equidistant to the decision boundary and are on the same side, they are classified as strongly positively. All right. If the distance from the boundary changes, then the degree to which they are classified on that side changes as well. Now we can use this and define the set of linear classifiers without the constraint that they have to go through origin. The only difference here is that we can now move the boundary, decision boundary, to be anywhere, not just those that go through origin. Again, we have an orientation of the boundary as well as the location. So the decision boundary here is now written in a vector form slightly differently. It's all x such that theta dot x, which is now that inner product is a scalar. We add a scalar parameter theta naught, offset parameter, and that whole thing equals 0. This is now the decision boundary. And it is theta naught here that controls the location of the boundary, where it is in relation to origin. And theta here controls the orientation of that boundary. So again, theta as a vector is orthogonal to the decision boundary here. So on this side of the boundary, again, theta dot x plus theta naught is positive. As every time we are on the same side as where theta points, then the linear function here gives us a positive value. It's exactly 0 along the boundary, and it's negative on the other side. Okay, now we can use this to define the set of linear classifiers without the constraint that it has to go through origin by defining that classifier now with two parameters, parameter vector theta, and that scalar theta naught offset parameter. And again, similarly saying that the label that's returned is just the sign of that linear function theta dot x plus theta naught. All right, you specify the two parameters, you specify the orientation of the line and where it's located. And we know which side is positive and which side is negative. Okay, so theta and theta naught fully specify the classifier. Again, the mapping is not unique. There are many theta and theta naughts that define the same decision boundary, but each classifier has now a set of parameters that correspond to the same decision boundary. And the whole set of such classifiers is then obtained by varying theta as a vector in general in RD and theta naught as a scalar parameter. So this is now the set of linear classifiers. Okay, so when we look for linear classifier, we try to find parameters theta and theta naught on the basis of the training set, and we want to select those parameters in such a way that the classifier makes correct decisions. All right, so to understand this a little bit more, let's look at whether in the figure that I drew, whether the theta naught scalar parameter here is positive or negative. So what is that value? We can just figure it out from this. If we take that linear function, we put origin in place of x. So we have theta dot now a 0 vector plus theta naught, and we see from the figure that this origin lies on the negative side, so this has to be negative, which implies, since this is now 0, that theta naught itself is negative. If we move this boundary in this direction past the origin, theta naught would become positive. All right. That is the set of linear classifiers through origin earlier, and now the full set of linear classifiers. Let's understand through examples how constrained the set of linear classifiers really is. So if we take a set of examples, the training set, and ask whether it's separable, whether there exists a linear classifier that correctly classifies all the training examples. If our training set looks like this, these are positively labeled points these are negatively labeled points, then there exists a linear classifier through origin that correctly classifies those points. Okay? If I take an example of another training set here, positively labeled points, negatively labeled points, these are no longer separable through origin. That is, there is no linear classifier through origin that correctly classifies these points. If we try to draw a linear classifier through origin to correctly classify these points, it would always misclassify some. But as a training set, it is still linearly separable. No longer through origin, but there is a linear classifier with that offset parameter that now correctly classifies those examples. Here's an example of just 4 points for which there is no linear classifier that correctly classifies those 4 points. Okay? I cannot find a linear classifier here that correctly classifies the positive labeled points without misclassifying one of the negatives, for example. All right? So this illustrates that the set of linear classifiers is actually quite constrained in the way that it can make decisions. And I can even find just 4 points in general positions such that the linear classifier no longer succeeds in finding a good solution. All right? So a little bit more formally, the training examples are said to be linearly separable if there exists a linear classifier that correctly classifies those training points. Okay? Put another way, if there exist parameter vectors theta hat and theta naught, scalar parameter theta naught hat, such that this linear function, its sign agrees with the given label. Okay? This product is positive when the classifier, the sign of this, would agree with the corresponding label y. So if there is a linear classifier in the set that would correctly classify those training points, then the training points are said to be linearly separable. And we've already seen cases where that linear separation does not succeed. So the set of linear classifiers is inherently constrained. All right. We defined earlier training error for any classifier as a fraction of training examples that are misclassified. So in terms of whether or not the classifier applied to the training example, whether it disagrees with the given label for that example. All right. We can now write this down for linear classifiers through origin slightly differently, since each classifier is specified by a parameter vector theta. We can think of evaluating a parameter vector in terms of its resulting training error, and it's again fraction of misclassified points by now a linear classifier. So I get the double brackets here, but now I'm saying just whether the given label, its sign agrees with the linear prediction. So if this is 0 or negative, then a linear classifier that is the sign of that dot product would be different from the given label. Okay? And note that when this is exactly 0, if the example lies exactly on the linear boundary, we count that as an error, since we don't know which way we should really classify that point. Okay? So that is now the training error expressed specifically for linear classifiers through origin. Okay? Now we can analogously define training error for linear classifier, general linear classifier as the fraction of misclassified points by looking at whether the given label agrees with the sign of the linear function used to define the linear classifier. If that is 0 or negative, then we call it an error. So linear classifier, general linear classifier, takes the sign of this. If that sign agrees with that, we get a positive one, so not an error. Otherwise, we call it an error, including the 0. We have now defined the set of linear classifiers. We understand how to parameterize it, and we have defined how to measure error for a set of linear classifiers, or for each linear classifier. We can now turn to the problem of actually finding a linear classifier that agrees with the training examples to the extent possible. To this end, we're going to progressively define a learning algorithm, perceptron algorithm, that takes in a training set and finds here initially parameter vector, only parameter vector theta, so a linear classifier through origin, that hopefully correctly classifies all the training examples. This algorithm will succeed if there exists any linear classifier through origin that correctly classifies the training examples, then the algorithm will find a solution to that problem. All right, so let's progressively define what this algorithm is and understand why it succeeds in finding a parameter vector that's actually reasonable. So we start with a 0 parameter vector. All the parameters are set to 0. Okay. Then we go through training examples, say take the ith example, and we check whether it is misclassified. Remember, this is the argument to the error when we just defined it, tailored the error for linear classifier. If this product here is 0 or negative, then the linear classifier makes an error. So if an error, then we do something, we update the parameters to correct for that error. Okay? And since parameter vectors are 0, this product is 0 initially, so the first example is always considered an error. Okay? So perceptron algorithm makes actually a very simple update to the parameters. So the parameters after the update are the parameters before plus label, scalar label plus minus 1 times the vector training example itself. Okay, very simple update to the parameter, okay, in response to any mistake. So we're going to try to understand this algebraically, why this update is actually doing something useful, and then later provide a geometric example demonstrating how that works. Okay, so let's look at whether an example that is misclassified on the basis of which we perform the update, whether it would be misclassified if reintroduced as an example at the next step. Okay, so then we would consider calculating an error, taking yi, the label here, and then parameter vector now, the old parameters, which are initially 0, plus yi and the example xi in a product with the example xi itself. So we are evaluating whether or not this would be negative or 0 after the update. Since the parameters are initially 0, we can just multiply this in. Label times itself is always 1, since the labels are plus minus 1. And vector in a product with itself gives you the squared norm of that vector. Okay, so what after the update we would get the squared norm of the vector itself. Okay, so initial example, always an error, and after the update, we get a positive value. So the same example would not, if reintroduced at the next step, would not be misclassified anymore. So the update algebraically is doing something useful. Okay, now what we going to do here over the whole training set is we start with the 0 parameter vector and then go over all the training examples. And if the ith example is a mistake, then we perform that update that we just discussed. Okay, so we nudge the parameters in the right direction based on an individual update. Now, since the different training examples might update the parameters in different directions, it is possible that the later updates actually make the earlier, undo some of the earlier updates, and some of the earlier examples are no longer correctly classified. So we have to go through the training set here multiple times, here capital T times, go through the training set either in order or select at random, look at whether it's a mistake, and perform a simple update. Okay, so this defines the whole perceptron procedure for linear classifiers through origin. It takes in as the training set. It's tailored for linear classifiers. Here it also takes in a parameter that tells you how many times you try to go over the training set. Okay. Now, theoretically, this classifier for sufficiently large T, if there exists a linear classifier through origin that correctly classifies the training examples, this simple, very simple algorithm actually will find a solution to that problem. There are many solutions typically, but this will find one. So for example, if here are the training examples, here's the coordinates, x1 and x2, here's the origin. The perceptron algorithm might find, say, this as the solution, but there would certainly be multiple different linear classifiers through origin that also work. Let's now look at a geometric example of how this algorithm works. So we start with a parameter vector that's all 0. Okay, we're given one example here. Let's say it's a positively labeled point. Okay, now perceptron algorithm sees that as a mistake. First example is always a mistake. So the updated parameters are now the old ones, which is just a 0, plus label for this example times the example itself. The label for this is +1, and this is the example. Okay, so the parameter vector after the first update is simply xi. Okay, so if this is now theta, it's the same as the example itself. The decision boundary goes orthogonal to that. Okay, so clearly that example is now on the positive side of the decision boundary. Okay, let's introduce another example. Let's make it a negative one here. Here, a negatively labeled point. Okay, it is misclassified. So the perceptron performs an update. So the update is theta plus now the, say, jth example, xj. This label is now negative. And here's just the example itself. And previously this was just xi. So as a result, we get xi minus xj as the resulting parameter vector after the update. So that would be then the vector here, going from the negative to the positive labeled points. So if we transport that parameter vector here to the origin, so the new parameter vector after the two updates is here, and the corresponding decision boundary is orthogonal to that and going here. So after the two updates, the perceptron algorithm, if these were the only 2 points, the perceptron algorithm would have found a solution that correctly classifies both of these points. All right, so it is possible you can easily come up with examples where the perceptron algorithm needs to go over the training set multiple times before a separable solution is found. All right, so now we can generalize the perceptron algorithm to run with the general class of linear classifiers with the offset parameter. The only difference here is that now we initialize the parameter vector to 0 as well as the scalar to 0, and we check the error as we did before, whether the classifier makes a mistake, now involving the offset parameter, and the update now involves updating the parameter vector theta exactly as before, but also updating the offset parameter in this way. So let's motivate how the offset parameter update arises here. If you think of set of linear classifiers here, let's take an arbitrary x, theta dot x plus theta naught. I can write this slightly differently, as if it were a linear classifier through origin, but taking slightly different examples. So I can write the parameter vector now, theta here, and add that scalar, theta naught, as the last coordinate here, and then write down the example and put 1 here as the last coordinate. Okay? So effectively, I can think of the linear classifiers with offset parameter as a linear classifier through origin, just operating on slightly different examples. Okay? So if you now look at this update equation here, it is actually in theta naught is updated by taking the previous values for those parameters plus label times an example exactly as here. Okay, so nothing is really different here in terms of the update. It's just a direct generalization of the perceptron algorithm without offset. All right, so now we have a general learning algorithm, the simplest one. And as I mentioned earlier, it can be generalized to be quite powerful and therefore a useful algorithm to understand. All right, so what are the key things to learn from this lecture? We talked about parametric families of classifiers, sets of classifiers. So when we look at a problem, classification problem in light of a training set, we define a set of classifiers, our choices from which we find a classifier that best fits the training set. We defined specifically what the set of linear classifiers is, how to parameterize linear classifiers. We talked about linear separation, when the set of linear classifiers is sufficient to separate the training set. We did that by means of examples. And we defined a learning algorithm for the set of linear classifiers that can take a training set as an input. If that training set is linearly separable, then the perceptron algorithm succeeds in finding a solution to the problem.